Welcome to number 5 in Drug Free Australia's series on cannabis epidemiology with Dr. Stuart Reece, world expert in population studies on cannabis and its effects. And today we're looking at cannabis and cancers, a pretty relevant kind of subject. Thanks, Stuart.
Well, thank you, Gary, for asking. Yeah, let's take a look at the cannabis and cancer subject, because this is a subject we started looking at this because the literature was ambiguous. There are positive and negative studies in literature, and we wondered what happens when we look at the really big populations, like all of Europe, all of America, and when we compare them directly. So that's what we're going to talk about today. Let's start talking about Europe. Now, just imagine you've got an x-axis there with the amount of tobacco smoked and a y-axis there with the amount of lung cancer. You'd expect the line to go straight up to the right, which we call a positive slope. So what this does is this is looking at tobacco on the x-axis and the various cancers there on the y-axis. And as you can see, for all these different cancers, and many of these here with a positive slope, are known to be linked with tobacco smoking, and that's why tobacco is regarded as a major public health risk factor for many different cancers. As you can see here, there's a strongly positive relationship. And when we use the same...
I'll just point out some of the cancers. Because the writing is so small on people's screen, you might, just so they get an idea.
Yeah, stomach, cervix, stomach, ovary, lung, kidney, pancreas, uterine body, all cancer, larynx, prostate, leukemia, and esophagus.
Okay, that's helpful.
Yeah. So they're the main ones which are positively related. And then we look at alcohol, and alcohol is also known to be a carcinogen. And we see the esophagus, cervix of the uterus, prostate, lung, all cancers, kidney, ovary, stomach, pancreas, breast, and larynx.
And Stuart, this all falls out of the same data set which you were using for cannabis, right? This is all the same data set.
That's right. So first we look at tobacco, and all these ones that are identified in this methodology are known to be tobacco related. And similarly here, all these ones here are known to be alcohol related. And then we look at last month cannabis, and we see that again, there's a lot of strongly positive related tumors. So we've got larynx, breast, myeloid leukemia, esophagus, gallbladder and biliary, lung, lymphoid leukemia, myeloma, liver, hepatocellular, parts of liver cancer, Hodgkin's disease, the bowel, large bowel, kidney. Those are the main ones that are positively related with cannabis.
Not pretty.
No. And then that's last month cannabis. This is daily cannabis, which is a different metric. And again, many of them are positively related, as you can see there.
So this is people who are using cannabis all the time versus occasionally on the previous.
That's right. And this is the herb, the THC content of cannabis herb. This is a different measure of cannabis exposure, and that again, there's about 14 cancers related there. The THC content of cannabis resin. That's
much more concentrated.
Yeah, there's about 11 cancers there. Now, this is a very interesting plot. This is called a bivariate chloropleth plot of breast cancer by cannabis herb THC concentration. Now, the way this works is obviously over these 20-year period, breast cancer has been mapped across Europe, and this is the color plane key here. Purple, pink is where both cannabis and breast cancer are common up there, as you can see. So the pink and purple, that's where it's together. And you can see that's Belgium, there is pink in 2001, and then Germany turns a bit pink. But by the 2020, the whole continent has gone pink as breast cancer and cannabis have together become more common.
That's an alarming picture.
So that is a very dramatic demonstration of the two covariates moving together across space and time in the way that we've outlined, which it's not just a correlation. It's not just saying they're correlated. They're actually co-occurring across space and time. And really the only way that could happen is if there's a causal relationship. So that's the whole continent is turning pink there, which is a very powerful message indeed. Now, in the USA, breast cancer by THC content, to some extent, we see a similar pattern. Breast cancer and THC in some states move together, and in other states, they did not. So that's interesting. And this is pancreas by herb THC content. Again, pancreas, we've done detailed studies in America. We've published this a couple of times, looking at cannabis and the pancreatic cancer. And in Europe, you can see that the two have moved together very closely. And here the whole continent is turning purple, which fits with the American data, which is a detailed study in America, they're moving together also when you consider ethnicity. Now, this is cannabis and pancreas and cannabinol. And again, the US is turning purple and pink. So pancreas cancer and cannabinol is another non-psychoactive cannabinoid. Now, if you divide the Europe into high and low cannabis-using countries, you find that the rate of cancer in the high cannabis-use countries is much, much more than the rate in the low cannabis-using countries. And the p-value here is 3 by 10 to the minus 135. Now, in science, p less than 0.05 is thought to be significant, and here it's 10 to the minus 135. This is a hugely significant result. Now, cannabis versus tobacco, alcohol, this is an additive panel model in Europe. What this shows, I'll just go through this slowly. This is the numbers of cancers implicated by substance. So the numbers of cancers found to be implicated by the substance were herb THC, last month cannabis, then tobacco, income, resin THC, and alcohol. So tobacco and alcohol are there, and the top two spots are measures of cannabis exposure. This is the total negative p-value exponents by substance, and herb THC is there, and the last month cannabis is there. Again, tobacco, income, alcohol, and resin THC. But this is the total p-value exponent. You can see that the significance of the herb THC and last month cannabis are far more significant than tobacco and alcohol on that metric. So this is the log of the total minimum E-values by substance. So this is the minimum E-value. The E-value is the expected value, which relates to causation. More than 1.25 suggests causation. And this is the log, the natural log of total minimum E-value exponents. So we've got last month cannabis, herb THC, resin THC, then income, tobacco, and alcohol. Tobacco and alcohol on this metric don't rate. And this is the total. This is the total. And these three measures of cannabis are much more powerful than tobacco and alcohol. And then if you look at the average, that was the total of the minimum E-values, is the average of the minimum E-values. So the E-value, the expected value, has a confidence interval, a 95% confidence interval, and the lower confidence interval, if it's removed from above 1, and that suggests that it's important. It's a measure of how powerful, how strong that effect is. And again, last month cannabis, herb THC, resin THC, the top three spots all go to measures of cannabis, and tobacco and alcohol don't rate on this. So that's the total, and that's the minimum, which shows that overall the cannabinoid metrics are far more significant carcinogens than are tobacco and alcohol across all those panels. Now we just jump across the Atlantic and look at America. Here we have cigarettes. There's cigarette use across there. And right as you'd expect, lung cancer is rising steeply. That's exactly what we'd expect to see. The more tobacco, the more lung cancer. You get a strongly positive sloping regression line, sloping positively upwards to the right. And then all these other cancers, as you can see there, are all link. That's what cigarettes looks like. Alcoholism looks like that. It's a less pronounced effect than tobacco, probably, in terms of numbers of tumours. Cannabis, you can see that some of these curves, thyroid, liver, breast, bladder, pancreas, and acute myeloid leukemia, all have strongly positive upward sloping lines. Then this is the THC content. Again, those same cancers are strongly related. Here, the oropharynx is also related. Chronic myeloid leukemia is also involved there, and kidney cancer, and probably myeloma is involved there, ALL as well. So cannabidiol, again, there's all these positive cancers related to cannabidiol exposure, including all cancer there, colorectal, bladder.
So how many would that be, seeing as CBD is so popular out there? How many would be where CBD would be causal in those cancers?
Well, it's strongly positive, significantly positively related with about 12 just on that, just looking at that graph.
Yeah.
So
Yeah.
all the details are in our papers, and the slides provide the references for those who want to dig deeper.
Correct.
Now liver cancer is a rapidly growing cancer in the US, and when you chart it, this is the bivariate plot again. You can see that in the Northeast, the Northwest, California, Washington, Oregon, California, Texas to a lesser extent, they're both strongly positive. Now that's important because a lot of this is attributed to viruses, hepatitis B, hepatitis C, immigration. We know that those viruses are more common in certain ethnic groups, and the changes in Texas may be related to increased immigration over the southern border. But the point is that cannabis has been largely overlooked. But the two are co-occurring across space and time, obviously, from that graph. And then when we look at liver cancer in Europe, we see a similar change, and we see the parts of the continent, France, Italy, and Spain, are all turning purple concurrently. Prostate and cannabidiol, the prostate cancer looks like that. That is positively related because both prostate cancer and cannabidiol were getting less common across the US over time. And that's probably related. That's partly artifactual because there's a lot of prostate cancer diagnosed when PSA screening was introduced. But you can see that in space and time, it's strongly correlated there. Prostate cancer in Europe, again, France, Sweden, Switzerland turning purple. That's Norway there. So you see the same thing. Now, prostate cancer by substances. So there's a strong relationship with cigarettes, a negative relationship with cannabis, a positive relationship with alcohol use disorder, that's alcoholism. Analgesics and cocaine is a weaker relationship. But when we look at the prostate cancer by cannabinoids, most of them it's negative, but with cannabidiol it's strongly positive. There's a positive relationship with cannabidiol. And now all these cancers can be modeled across time, which this is breast cancer at 1 spatial and 4 temporal lags. You lag it by a year or 4 years in that case, and that's breast cancer at 4 lags, brain cancer at 1 spatial and 4 temporal lags, ovary cancer at 6 temporal lags.
So just explain the lags a little bit, Stuart, because that's kind of important.
Yeah, well, cancer is a disease. It doesn't develop straight away after exposure to a carcinogen. It takes a number of years for the cellular changes to develop and for those transformed cells to multiply up and become an invasive cancer. So it's common in epidemiology to conduct, it's called a lagged analysis by 2, 4, 6, 8 years, whatever.
Yeah, so when you're comparing this with cannabis use in a particular year, then the lag for that cannabis use to take effect.
That's
All
right.
right.
That's
Yep.
right. And these models are derived from geospatial models, from space-time models, and all these can be calculated from the models which are presented in our book and summarized. Now, for some of those models, there's a negative relationship, obviously, here. But for many of them, it's a very strongly positive relationship. For many, this looks like a cubic curve. That's what a cubic polynomial curve looks like, and this looks like an exponential curve. So it's just the way the cookies crumble. And this here we fitted a cubic to these lines, which give pretty good degrees of fit. This is the E values from the graphics for the cubics. This is the high value. This is the log of the minimum E value. So this is E to the 80. So it's very high E value. And then
so strongly causal.
Yeah, that's right. And then as you reduce all these other models, you get cubic, so you get 2 and 3 E values there. So this is showing that these E values are this is a log, they're strongly related. And then this is ANOVA, this is an ANOVA. This is comparing the linear and the cubic model, showing that the cubic model provides a better fit. In other words, at the higher doses, you get this big kick in effect. There's a big uptick in cancer incidence at the higher incidence. Right. So when you increase, cannabis exposure, often through legalization, there's a big uptick in cancer incidence occurs. That's what this is showing. This is the prevalence ratio of cannabis quintiles, 1 versus 5. What that means is we're dividing cannabis exposure here into 5 different groups, 5 equally spaced groups. They're called quintiles because there's 5 of them. So this is looking at the rate of these cancers in the highest versus the lowest cannabis quintiles. And you can see for all these cancers, this is the one line where no effect, but for all these cancers, it's significantly elevated.
So that's all about cannabis use, high cannabis use versus low cannabis use.
The highest versus the lowest quintiles.
That's it. Okay.
And then this is the attributable fraction in the exposed and the attributable fraction and the attributable fraction in the population, or the population attributable risk, which are classic indices which epidemiologists use. And this shows that for bladder cancer, it's about 20%, almost 20% of the attributable fraction in the exposed can be attributed to cannabis using this technique. And same for all the others like that. And then this is the prevalence ratios by different cannabis legal status. So this is illegal versus liberal, and you can see for melanoma it's higher there, liver, thyroid, uterine, corpus, stomach, a lot of the cancers we talked about before. In the liberal status, it's more frequent. And then this is medical versus illegal. The medical cannabis for melanoma, it's higher, looks like that.
Just go back to your liberal. Liberal includes medical cannabis or just decriminalised cannabis and legalised cannabis?
No, illegal versus everything else.
Everything else. Okay. All right. So medical cannabis can be in there, and then you break that one out separately.
Yeah, that's right.
Okay. Got it.
And then this is liberal versus illegal. This is attributable fraction in the exposed and the population attributable risk by cancer type. These are age-adjusted rates. This is CDC cancer data taken direct from the CDC. It's not manipulated in any way. This is liberal versus illegal, and so for these cancers, it's more common in the liberal cannabis liberal states. And this is the population attributable risk, the attributable fraction in the whole population.
Mm.
Now, this is the case fraction summary using different measures of the fraction if this is the carcinogen, decriminalised cannabis, liberal cannabis, cannabis quintiles, medical cannabis, cigarettes, alcoholism, and obesity, because obesity is cancerogenic.
Okay.
So this is if you assume a attributable fraction of 1, which is probably excessive. And this is an attributable fraction in the exposed. Again, cannabis, quintiles, obesity, cigarettes, liberal cannabis, medical cannabis, decriminalised cannabis, and alcoholism there. So the cannabis indices are there, cannabis quintiles are there, and cigarettes is there, alcohol is there. And then this is the attributable fraction is the population attributable fraction, or the attributable fraction in the whole population. So you can see that's 80%, that's 6%, that's 2%. And of course, this will rise, the population attributable fraction will rise as the cannabis use in the population rises, probably towards the attributable fraction in the exposed, because more of the population are exposed to the intoxicant. So again, here you've got liberal cannabis, obesity, cigarettes, cannabis quintiles, decriminalised cannabis, and alcohol use disorder. Cigarettes is there, so cannabis is there. So in each of these different measures, the cannabis indices outperform or are more significant than cigarettes and alcohol. If you look at that closely, that's the take home.
Okay, that's good summary.
Message from the picture. So this is the total cancers from the CDC list: the cannabis, obesity, tobacco, alcohol, and HPV virus, the human papillomavirus. the totals there on this metric, this is the trivial fraction of 1, is higher for cannabis than tobacco and alcohol. This is a case number summary by model type etiological fraction. The etiological fraction is the trivial fraction in the exposed by the cannabis quintiles. And you can work out how many cancers from all of that. Cannabidiol, related cancers, 52,000. Total cancers. This is the causal inference by bivariate spatial models, multivariate spatial models, causal models, and geospatial. So you're getting a total cancer. That's the total cancers reported in the US, nearly 2 million for this year, and about 150 to 170,000 of those could have been related in these different models to cannabis, which is about 8 to 9%, 2% for cannabidiol.
Wow.
So that's important. And then this is the epigenetic summary. We've talked about the fantastic epigenome-wide association study from North Carolina. And if you look at that, the genes identified in the SHROT database, there are 20,000 genes identified in that database. And the pan-cancer overall, so 40% of the pan-cancer, that's all the cancers, cancer driver genes, 30%, myeloid leukemia, medulloblastoma is a brain cancer, mitochondrial genes, these are Cell and Nature, some of the top journals in the world.
We need to just refer our audience back to our last 2 episodes. When you're talking about SHROT, that's where you'll find good explanation.
Yeah, SHROT she was the first author on the North Carolina Epigenome-Wide Association study paper a couple of years ago.
Okay.
So we've looked at America, we've looked at Europe. The question is, how do these two match up? Because if cannabis is really causal in these tumours, then you expect there to be a close correlation. Now, it's a bit tricky because Europe count more cancers than America. So there can't possibly be a one-to-one relationship. But if you look, these are the minimum p-values. And this is the study, whether it was categorical study or continuous study. This is correlate that was studied in the US. You can see that there's a remarkable degree of overlap. You know, you've got brain medulloblastoma and brain cancer, breast cancer in both places, chronic lymphoid leukemia in both places, chronic myeloid leukemia, ALL, AML there, all cancers measured in the US. It wasn't measured in Europe. Oropharyngeal cancer is there with highly significant p-values, non-Hodgkin's lymphoma. So you can see there's a lot of overlap. That is not a random pattern of overlap. Now, again, if you go to the EWAS study we're talking about, the Epigenome-Wide Association study, and you look at the number of genes linked with each cancer type, you can see it looks like that. This is cannabis dependence. This is the cumulative number of genes. And this is a negative log p-value by cancer type in cannabis dependence. You can see all these different cancers are involved. And if we do the same thing in cannabis withdrawal, interestingly, it doesn't go away to 0. There's still a lot of genes in each of these tumor types. This is the cumulative gene number. This is a negative log p-value. So that's, if you look, that is 400 there, and it's 300 there. That's 3,000 there, and it's 1,000 there. So cannabis withdrawal reduces the effect, but it's still a very significant and substantial effect. The p-values in dependence and withdrawal, see the p-values drop. Here's 10 to the minus 15. There's 10 to the minus 5. So in withdrawal, it improved, but it's still highly significant. Now, what's fascinating to us is this is what the data look like that we've been charting to help us read. It's a bit data dense. But if you look at the gene ratio in dependence to withdrawal, so in dependence for this cancer, ALL, which is the major childhood cancer, acute lymphoid leukemia, the p-value ratio dependence withdrawal is that. Total gene number in dependence is 23, but the total gene number in withdrawal is 118. In other words, and so the ratio of the gene number independence to withdrawal is about 0.2. So there's about 5 times as many genes activated in ALL in cannabis withdrawal as cannabis dependence. And you see the same sort of thing happening with AML, acute myeloid leukemia, where you go from 11 genes to 36 genes, which is 3 times more.
So that's kind of counterintuitive. You would expect that there's some kind of repair happening and there are going to be less changes to genes, but that's not the case.
No, that's an oversimplification, Gary. You would expect it to improve, and sure, that's the overall pattern. But within that, some things get worse.
Yeah, okay.
What's very significant, what's very interesting to us is that there are epidemiological studies which link in the US, which link childhood ALL with prenatal cannabis exposure. And there's several studies linking childhood AML. There's 3 or 4 studies linking childhood AML with prenatal cannabis exposure.
Yeah, okay. That's alarming.
Now, in other words, this explains something profound. What this is saying is that cannabis withdrawal triggers leukemogenic gene cassettes. So the genes that cause leukemia are triggered by cannabis withdrawal. And that's true for ALL and AML. And that's confirmed in the epidemiology. Now, that's relevant to babies being born because we've talked about birth defects from cannabis. But if you think about a baby who's born to a cannabis-consuming mother, the baby goes into cannabis withdrawal. And it may be that cannabis withdrawal that triggers the leukemia in the offspring.
Goodness.
And this is how it happens. And this explains there's studies showing that, and 3 or 4 studies showing that kick up following birth. And this may be why. I mean, it's not proven, but the pattern that we're seeing here, it's fascinating that these two, which are linked with, these are the 2 congenital cannabis cancers, 2 of the congenital cannabis cancers. The only ones on the list, the other ones linked with congenital exposure are so rare that we don't have data for them. But it's fascinating to us. Does this represent activation of leukemogenic gene cassettes by the cannabis withdrawal associated with the birthing process? And is that what's causing these leukemias to occur in these offspring?
Okay.
And so here we're just making that dramatically obvious. These are the different cancers. That's dependence, that's withdrawal, and this is the ratio of dependence withdrawal. And you can see that for ALL and AML, this ratio really kicks up in a big way in withdrawal, which could be what we're seeing epidemiologically. In other words, cannabinoid genotoxicity causes cancers and is expressed as cancer, and cancerogenesis is a major manifestation of cannabis. And with things like breast cancer, which is becoming more common, is been shown to be a driver. And with pancreas and liver cancer, which are growing quickly, has also been shown to be driving those 2 cancers, which are growing quickly, but is largely an overlooked environmental carcinogen in the literature thus far.
So just to summarise, we have 16 cancers that are tied up with tobacco. And what is it for alcohol? 9, maybe?
Yeah.
I think it's 9. How many for cannabis are you finding in those populations?
Well, it depends, Gary, how you study them. I mean, please refer to our papers for details. But what we just saw was cannabis. There's about 12, THC is about 8 or 9, and cannabidiol is about 9. So it depends how you count and what you count them.
Okay.
But you can see that when we compared tobacco and cannabis and alcohol directly, and even obesity, that cannabis outperformed the others as environmental carcinogens. And that's an important take-home message with a major public health.
Okay. And also to summarise, when you're looking at disease burden of alcohol and tobacco when it comes to cancers, how does cannabis compare to those 2 as a summary?
It's much more significant.
There we go. I think that's as much as we need to know.